Good afternoon, honored guests. On behalf of the Civil and Environmental Engineering Society, University of Jaffna, we extend a very warm welcome to each of you as we gather here for Symposium 2026. This year, our event is centered around a vital name, multifaceted and environmental engineering. We are delighted to have you join us this afternoon to explore these diverse ideas and innovations. Please do take your seats as our proceedings will begin. With light comes hope. Let's begin by lighting of the traditional oil lamp, a symbol that has long represented the dispelling of darkness by the light of knowledge. May I request our invited dignitaries to kindly join us for this auspicious moment.
May I invite Dr. K. Kaneshwaran, Dean of the Faculty of Engineering, University of Jaffna. Thank you. Professor D. N. Subramaniam, Head of the Department of Civil and Environmental Engineering. Thank you. Thank you. Dr. Mrs. P. Jayananthan, Head of the Department of Computer Engineering. Thank you. Professor T. Thiruvarun, Head of the Department of Electrical and Electronic Engineering. Thank you. Dr. V. Mugilkithan, Head of the Department of Mechanical and Process Engineering. Thank you. Professor N. Sadibaran, Partner of Civil and Environmental Engineering Society. Thank you. We invite our technical section chairs, Mrs. P. Sangida and Mr. S. Kishodhar. Thank you. We invite a representative of our sponsor, Tokyo Cement Company Lanka PLC. Thank you. Mr. K. Rishikeshan, President of Civil and Environmental Engineering Society. Thank you. Mr. M. Sajivan, Chief Editor of Civil and Environmental Engineering Society. Thank you. Now we invite one of the presenters to come forward for the line. Thank you. As the flame is lit, we are reminded that engineering in its trusted form a pursuit of clarity. Thank you. Now we invite all present to rise for the singing of the national anthem. Thank you. Please be seated. It is our privilege to invite Professor D.N. Subramaniam, Head of the Department of Civil and Environmental Engineering, to deliver the welcome address.
A very good afternoon to everyone. It's my great pleasure and privilege to welcome you all to the third Undergraduate Research Symposium of Department of Civil Engineering. I warmly welcome our chief guest, the Dean of the Faculty of Engineering, our distinguished keynote speaker, Professor H.R. Pasindu of University of Moratuwa, the heads of the departments of Faculty of Engineering, our special invitees, academic colleagues, members of the support staff of the Department of Civil Engineering, and most importantly, our students. I also extend a very warm welcome to everyone joining us through Zoom and watching the symposium through our YouTube live stream. Though we may be participating from different locations, we are united today by a shared commitment to knowledge, innovation, and the advancement of civil engineering. An undergraduate research symposium is more than a platform for presenting findings. It is where students learn to question accepted ideas, investigate real problems, defend their reasoning, and communicate solutions that may contribute to a better society. Today, we celebrate not only completed research, but also the intellectual journey behind it, the uncertainties faced, the failures overcome, the questions refined, and the confidence gained. Every presentation represents a student who has moved beyond learning what is already known and has taken the first step towards discovering what might yet be possible. I sincerely appreciate the dedication of our students, supervisors, academic and support staff, organizers, and everyone whose commitment has made this symposium possible. May today's discussion inspire new ideas, meaningful collaborations, and a deeper sense of responsibility towards our profession and society. The value of research is not measured only by the answers it provides, but by the better questions it inspires us to ask. I warmly welcome you all and wish the third undergraduate research symposium every success. Thank you.
Thank you, Professor, for those gracious words as we open this year's symposium. Symposium 2026 would not be possible without the generous support of our valued sponsor. We would now like to acknowledge the generous support of our sponsor, Tokyo Cement Company, Lanka PLC, whose contribution has greatly assisted in making today's symposium possible. So, ladies and gentlemen, please direct your attention to the screen for our sponsor promotion.
Sorry for the inconvenience. Today, our keynote address will be delivered online. And before we begin, we would like to properly welcome our speaker into today's proceedings. We invite the Department Civil Engineering to the stage to connect with and personally welcome Professor H.R. Pasintu and to brief him on the proceedings so far.
It is my distinct privilege to introduce the keynote speaker of the third Undergraduate Research Symposium, Professor H.R. Pasindu, Professor in Civil Engineering in the Transportation Engineering Group of the Department of Civil Engineering, University of Morotto. Professor Pasindu is a distinguished academic, researcher, transportation engineer, and infrastructure specialist whose work lies at the interface of pavement engineering, transportation systems, highway planning, road asset management, infrastructure safety, and risk-informed engineering decision-making. He obtained his Bachelor of Science Honours degree in Civil Engineering from University of Morotto and subsequently earned his PhD from the National University of Singapore. His academic expertise is further strengthened by valuable professional experience as an executive engineer in the Road Infrastructure Management Division of the Land Transport Authority of Singapore. Beyond teaching and research, Professor Pasindu has made important contributions to academic leadership and national infrastructure development. He has served as director of the Engineering Research Unit of the University of Morotto and currently serves as a research coordinator of Department of Civil Engineering. He has also contributed to major national initiatives related to road safety, highway development, transport planning, infrastructure investment, and accident data management. His recognition as an AAC Outstanding Reviewer, his receipt of multiple University of Morocco Research Awards, and his involvement in professional and scientific committees reflect the quality, relevance, and impact of his academic contributions. For our undergraduate researchers, Professor Pasindu represent an important example of how rigorous engineering research can connect fundamental theory, advanced analytical methods, field evidence, professional practice, and national development. Ladies and gentlemen, it is my great honor to invite Professor H.R. Pasindu to deliver the keynote address of the third Undergraduate Research Symposium. Professor Pasindu, the floor is yours.
Thank you, Dean, for the kind introduction. Very happy to be able to do a keynote at the symposium. So I think I will start my session. Let me share the screen. We also have a power cut, so just managing. Okay, right. So as Professor Char Pasindu from Department of Civil Engineering, University of Morotto. I also served as the president of the Chartered Institute of Logistics and Transport, Sri Lanka. So my talk today will center around introducing to you the domain of uh, transportation engineering. Is my voice enough, audible enough? Hello. Yes, audible. Yeah. So I'll be presenting on transport engineering and explaining where it sits in the broader field of civil engineering. As also as undergraduate students, what are your career opportunities and pathways in this field? So that is the main theme of my keynote talk today. So transportation engineering, if you want to define it, um, we are studying what we call transport systems, and everyone almost every day uses a transport system. I think all of you would have used a transport system. And how do we characterize a transport system? We characterize using three key components. For a transport system to exist, these three components should exist. Those are the fixed facilities, flow entities, and the control systems. And the interaction of these three will be what we call manifest in a transport system. So my aim in this talk is to explain within this broader area of transportation or transport system, where does transport engineering or civil engineering related component fit in, right? So there's aspects of civil engineering in all these three elements: fixed facilities, flow entities, as well as control systems. So during the talk, we'll try to see where all these things fit. Right. So the common misconception among a lot of civil engineering students is that transport engineering is confined to road construction, which is not the case. It is only a part of transport engineering. Under highway engineering, you do road construction, and that's a lot of that does comprise a major component of the domain, but it is not the only component of the domain, right? So that's a common misconception when people ask, what are you doing? You're doing transportation engineering. They assume that is just road construction, road building. But during this, you'll realize that it's much broader than that. More vast areas of disciplines can be covered under transport engineering. Okay, so before we go into the career paths and all that, let's try to understand what is this transport system and how these three components interact. That is the fixed facilities, the flow entities, as well as the control systems. So if you really look at it, the fixed facilities are the infrastructure that we see. Your roads, the junctions, the bridges, footpaths, the bus terminals, airports, ports, all those are fixed facilities. That's where the engineering input, infrastructure engineering or civil engineering input has the greatest impact on designing, constructing, and managing these fixed facilities. And then on these fixed facilities, you have flow entities. That is the moving component. Now, for example, on a road, you will see vehicles. In an airport, you will see aircrafts. On a pedestrian walkway or a footpath, you will see people. That is the moving entity. We call it the flow entity, the units that move through the fixed facilities. And the last, but perhaps the most important component is now when you have these moving components on these fixed facilities, there has to be some rules, right? There has to be some control over it. Otherwise, you will have a lot of issues. You will, first of all, you have safety issues. There'll be accidents and other hazards. And also, if you do not have rules, if you don't have a rule-based system, the system will not operate in an efficient manner. And that is where the signals, traffic signs, your bus schedules, timings, aircraft control systems, port navigation systems, all of those come into the picture to ensure these flow entities use the fixed facilities primarily in a safe and efficient manner. So if you bring down the transportation engineering to ask, okay, what are you trying to do as transportation engineers? We are trying to design systems where people or vehicles can use it in a safe and efficient manner. So once you guarantee that, you say that this transport system is functioning well. And when you break down, when that system breaks down, one of the first indications of a system malfunctioning is the fact that the transport system is now not safe, nor is it efficient. So if you look at local examples, a congested junction, a poorly planned road, you would see that the system is, a lot of accidents are there, a lot of congestion is there. That means the system is no longer functioning as we have expected, right? So either the design is faulty or operation is not following the control systems or the expected control. So this is the problem. So every transport problem, you can break it down to these three elements and see how these three elements are interacting. And civil engineers will have a role to play in fixing one or more of these components, right? Okay, so these are fixed facilities. I've explained earlier your railway tracks, your expressways, ports, terminals, runways. All these facilities are there, and not only that, in order for these fixed facilities to be constructed, you need supporting infrastructure. You need your retaining walls, you need your drainage, you need your embankments, all those supporting infrastructure, make sure these things can be provided. So that's where other domains of civil engineering come into the play. And it can be storage as well, your car park, apron area in a airport. All these are fixed facilities. The challenge is why we are putting a lot of effort in designing and planning these things is they're capital intensive, right? Whenever we're talking about an expressway project, we are talking about $1 or $2 billion of US dollars, right? These are not cheap. So if you make mistakes, the repercussions are also very expensive. If you end up with a poorly designed runway, it will affect the airport operations. So when you are doing this capital intensive project, you have to make sure these are designed, first planned and designed as well as possible. And the other one is you are designing for a very long period. In hydraulic structures, you are designing for perhaps 50, 100 years, right? Most transport infrastructure designed for more than 20 years. So a very long design life. And the challenge that is you have to be able to forecast. You have to be able to forecast the demand in 20 years' time. How many people will use this fixed facility and design it accordingly. You can't just design for the next year. You have to design for 20 years. You design for 30 years. And unlike things like hydraulic infrastructure, where it's somewhat controlled, I mean, predictable. These are very dynamic because you're mostly dealing with human behavior. It's going to change. A lot of global impacts is going to change. You might design an airport for 2 million passengers, but there's next global war or a medical emergency, you're not getting that, right? Or the economy might boom and you get more people. So very high probability that your demand will exceed your capacity. So you have to plan this very carefully. Effect is irreversible, right? So if you do a bad road, reinstating that to the original condition is very, very difficult. And the damage on the environment, the society, all those are almost irreversible. So you have to make sure you plan it properly, and when you're doing it, you do it right, right? So that's about fixed facilities. So few examples from Europe, you have some very good examples in Europe how various modes of transport are integrated in one area through fixed facility design, basically making sure you can run your trams, your bicycles, people walk, go in cars, all in the same space because that's how they have designed it. Flow entities, I don't need to explain too much. All types of movement, whether it's a ship or a plane or a bicycle, you're walking, anything, your goods, freight, everything is part of this broader definition of flow entities, right? So you can have flow entities on guided tracks. You can have flow entities that move freely. Now, people inside the terminal, that's a flow entity. So if a civil engineer is designing a terminal, our primary demand is from these people movement. So we had to figure out where these people are coming, how many people, how will they concentrate, what is the speed at which they will move, right? How much time they need to board, how much time they need to alight, how long does it take to issue a ticket. All these are parameters that we'll take into account in designing the size of this terminal, right? It doesn't come, it's not this random thing that people figure out, this is the size. And a lot of calculations go into determining this. There are standards developed by various agencies to help you do that. But a lot of the time, you go through fundamental analysis to figure out these things. Because as I mentioned, human behavior, we are designing, incorporating a lot of human behavior, right? So it can change. It can change, and that change will affect your entire operations, right? The other thing is, how do you measure fixed facility? I mean, sorry, flow entity movement. We talk about a rate or a flow rate, right? We talk about vehicles. If it's moving on a lane, we say vehicles per hour, right? So it might be on a per lane, you can move about 1,800 vehicles per hour if things are operating well. But when the traffic breaks down, when you call it, it's congested or gridlock condition. This vehicle flow from 1,800 per hour goes down to about 200, 300 passenger cars per hour. That's when you call it, it's congested. We call it traffic block. So we have to measure this. We have to measure the flow entity movement in order to understand how well the fixed facilities perform. So the last one is the control system. The control system is perhaps the most complicated one to design because you have to keep in mind what is the function of the fixed facility and how the flow entities can be manipulated or maneuvered in a way that the best possible uh, operational efficiency from the flow entity can be achieved. Now, for example, if you are designing a low volume road within a, let's say, housing scheme, you don't want people to go very fast, right? The roads are not designed for that. So you do certain changes in the road geometry to make sure people drive slowly. Right? You might put a speed hump, change the width of the road, you might put signs, you might put some these markings on the road. You might put some landscaping related work to change how people feel about driving so that naturally it will be controlled, right? At a junction, you know that if you have intersecting movements, there will be congestion. So you put a traffic signal and make sure you give right of way through the signal so that there won't be conflicts, right? Even things like regulation, pricing. Now, for example, in certain cities, you put a toll to make sure if you are entering the city during congested time periods, peak periods, you have to pay additional a fee. So that will discourage people from entering the city at that particular time period. So those are all part of control systems. Now, for example, our expressways have control systems. The first thing is you can enter the expressway at only a designated location, not like a local road where you can turn in and out anywhere you want. Before you enter, you have to get a ticket, right? Only certain types of vehicles are allowed to enter the expressway. There are control systems where it says you cannot park on the side of the road unless it's emergency, right? Unlike normal roads, you just park. Most of the roads you can park unless there's a sign indicating prohibiting. So control systems are very necessary, as I mentioned earlier, to make sure number one is safe. We have to make sure the flow entities are able to use these fixed facilities without harming themselves as well as harming another entity, right? That's why you put a guardrail or a sign at a curvature at a road curve to make sure people slow down or understand the speed at which they could take this curve to prevent them from harming themselves, or you prevent them from harming someone else. So number one priority in transport infrastructure design is safety. Once you guarantee safety, then you look at, okay, how can we make it more efficient, right? As in the case of a traffic signal. So if you allow people to decide who will get priority at an intersection, it will be chaos. No one's going to give way to the other person. It will be complete chaos. It'll work when there's less amount of traffic, but if you have a lot of traffic, it won't work, right? So it will be inefficient. So what you do is you create that efficiency through this control system that is a traffic signal, right? So we'll later on we'll discuss how civil engineering has a component determining this control system under for various fixed facilities. So these are some examples. You have your traditional traffic signage, road markings. In a railway, you have the signals. In an airport, in a railway, if you go to the railway station, the HQ, you'll see the big panel where they control all the train movements. So they are managing, right? The trains by themselves cannot manage the movement, right? So there has to be a central place where they control this. So air traffic control center. Now, if you look at the image below on the second row, you can see our airspace is quite huge, right? It goes all the way up to the Indonesian airspace. So massive area that is under Sri Lanka's control. So all aircraft movements within this, although there is no fixed facility per se, is controlled, right? Aircrafts cannot pick and choose whatever route they want. They have to coordinate with the ATC and keep to that specific route, right? So that flow entity is controlled through the control system, right? So effectively they are giving lanes of movement. Right. So now we discussed, you have a fair idea of what these three components are: fixed facilities and control systems and flow entities. So whatever it is, you have to plan, you have to design, you have to build, and you have to operate. I mean, that any engineering aspect, that is the process. No, you plan something, you design something, and build and operate. So if you take fixed facilities, that is completely within our domain, right? So all our fixed facility planning predominantly done by civil engineers, transport engineers. Designing, most of the time it's done by transportation engineering professionals. Building, it's just civil engineering, it's infrastructure, right? So massive input there. Operations also to an extent, ports and airport not so much, but other transport infrastructure, civil engineering has some role to play in how they are done. Control system building, of course, it's not civil engineering, it's electronics, that side, mechanical, electrical domain. But planning, for example, figuring out that the timing of signals, where do you install a traffic signal, those kinds of things, definitely civil engineers or transport engineers will do it. Operations also, you have to constantly update the timing depending on the traffic flow patterns. So there is some element of civil engineering involvement there. Flow entities, not so much. I mean, flow entities is automotive engineering. So it's design, definitely build, very minimum impact. Operations, there will be some input. Things like optimizing work will be there. A bit of planning input as well. But predominantly our domain within these transport systems are within design, build and operate fixed facilities. Moving ahead, there will be bigger component, bigger involvement for civil engineers in operating fixed facilities, because now our infrastructure is quite mature. If you look at our road network, most of the road rehabilitations were done about 20 years ago, 10 to 20 years ago. So they are now reaching that stage where you have to constantly maintain them a bit more. So operations wise, there'll be a huge role to play for civil engineers. Right. So where does transport engineering fit in within civil engineering and outside? Because transport engineering has a multidisciplinary element involved. From mathematics to behavioral foundations, a lot of operation research related work is involved. Obviously, probability and statistics now with machine learning, it's taken over. You have the transport science and modeling. So traffic flow theory, queuing theory, discrete choice modeling, demand forecasting, micro simulations, numerical modeling, basically. So those are part and parcel of this transportation. And then you go to the hard physical engineering part. That's where your geotechnical, geometric design, drainage, hydrology, surveying, those will come, bridge engineering. And then the systems part. You have a discipline called systems engineering in most universities. And part of that will come into traffic operations, public transport planning, intelligent transport systems, asset management, where you're optimizing the maintenance of assets. And beyond that, now this is not directly taught at undergraduate level, but when you're practicing as a transport engineer, you have to have a fair idea about transport economics, the cost benefit of doing these projects. We always talk about it. People complain, do we have to do expressways? Does the government have to run a railway operations? They are making a lot of losses. Who makes that decision, and why should we do that? And that is down to transport economics. So it's not taught a lot at undergraduate level, mostly at postgraduate level, but it's, if you're practicing, this becomes a major component for assessing transport projects. And then you have to be conscious about the environment, emissions, and ecology, equity, accessibility, disability access, women's rights, all part very, very strong components in planning transport infrastructure. Safety science, and a lot of inputs coming from urban planning. Town and country planning, or we call it urban planning. It has to go in parallel, transportation and urban planning. So in order to work with urban planners, you have to have some understanding about that as well. But these are not discussed a lot at undergraduate level, obvious time restrictions. But civil engineering core, the middle three, your transport science and modeling, physical engineering, and systems part is, at least some of them are covered. I think in all engineering programs, about 50% of these are covered to some extent. And the other way of looking at transportation is looking at the subdisciplines of transportation. That is, you have planning, you have traffic, then you have the highway design, and you have the pavement design, that is the soil or the structural design. So if you go further up, that means less involvement for civil engineering. If you go further down, that is more down to the core civil domain, right? If you go to the very classical universities, they will not have even transportation. They'll have a geotechnics or geotechnical engineering department that will take over pavement design component, right? So you don't have a specialized division for that. So at least in most civil engineering programs, you will have geometric design and pavement design. But if you are doing electives, most of the time you'll have planning, and you have traffic engineering modules as well. But if you go to schools like Delft, for example, they have a faculty of civil engineering. So within transport, they cover a lot at undergraduate level also. So then they are touching on things like social sciences, economics, systems engineering. There's a good school in Dresden, Germany, massive transport engineering faculty there. So they are looking at ecology aspects as well. It all depends on the focus of the degree program. That's the main thing. Right. So this is what we discussed earlier about a junction. So when you're designing a junction, there's so much interaction with you have to do modeling, you have to figure out simulations, you have to figure out how this traffic will behave once it operations. You have to do some designs, you have to check the distance, whether the visibility is there. Then you have to design the number of lanes, see whether people are crossing. Obviously, there'll be some hydraulic input, because you have to look at the drainage side of it. You have to look at the soil condition, and when you are constructing the road. So that's why I said it brings all the subdisciplines of civil engineering into the picture when you're doing a transport related project, right? So junction, as I mentioned earlier, is the best example to demonstrate what these transport systems are. You have the flow entities; those are the cars that are moving. You have the fixed facilities, that is the two approach lanes, the turning lane, all these other infrastructure, and the control system, the signs, the lane markings, the traffic signal. If you have a bus priority, you can have a separate bus lane, for example. If you remember, certain junctions in Colombo, you have a separate bus lane at the junction. So those are all controlling the movement of flow entities, but making sure you keep all those within the fixed facility design parameters, right? Yeah, so this is what I was just talking about, vehicle movement. And when, very interesting area in transportation is the study of vehicle movement. It's very similar to hydraulic, what do you call, the pipe flow equation, right? You have flow estimation as product of area of the pipe as the velocity. So it's very similar to that. Our velocity is the velocity of the vehicles, average velocity. We don't say area, but we look at something called density of the vehicles. That means per kilometer, how many vehicles are there. Now, in the picture that I've shown you here, you can see high density. That means per kilometer, you have a lot of vehicles. What happens is that when you have high density, your speed will slow down naturally. So it's mathematically proven as shown in the figure next to you. So traffic flow theory is rooted in this fundamental concept, right? A study of the movement of vehicles. And from this point onwards, you can develop all kinds of complicated equations. You can do numerical modeling, to create, I mean, develop software and analyze it using software. But it's rooted in this fundamental concept of studying the behavior of vehicle movement and how the speed and the density of the vehicle flow will change, right? Because those are related, right? So this is very much closer to the mathematics side of transportation engineering. But a lot of the earlier professors, the people who came up with these traffic flow theories were mathematicians, right? So they are coming from that background. But now we are adapting to solve our problems. The other one is about the demand estimation. How do you design a road? You look at the land use, and this is why I said you have to work with urban planners, because this is their domain, land use and activity planning. And then from the demographic data, population, age, income level, you have to figure out how many trips will be generated, how many movements will take place. So you have to understand about general economics and see, what triggers trips or what triggers vehicle movement. Then estimate from where to where these trips are going, and then obviously they will use a particular route, and that's where the congestion and delay happen. And that's how you have to plan. You have to plan for new facilities, right? So when you have delays or congested roads, you figure out whether you want to add a new road, or you have to put traffic signals, or figure out some other solution for that. So this is another main component of transportation engineering, looking at demand, how the demand evolves from trip generation up to how vehicles are assigned to a particular route, right? So we, for example, when the Ruanpur Expressway was done, you do a model for the entire study area. Find out, okay, if we were to develop an expressway from up to Ratnapur, what type of locations will it serve? Will it serve people living in Colombo? Will it serve people living further south of Colombo? Where will they try to go? Or will they try to just to go to Ratnapura? Or will they go further down towards Hambantota? So all this modeling type of work can be done using transport flow analysis. So, small problem. We don't have power, so my electric battery is down. I will change my computer. Just give me a couple of minutes. I'll swap my computer, right?
Okay, sir.
Yeah, you can see, no? Okay. Few more slides. I'll quickly. Yeah, so as I was continuing, you can finally end up estimating how many vehicles will be assigned to the expressway, and that you move ahead with the design stage afterwards. Right? Same with the road design. If you want to design a road surface, you build it up from the natural ground all the way up. And along that, you have to know about your soil mechanics. You have to know about drainage. You have to estimate how many traffic will go on the road and what their loads will be. And you can see the different layers. And then once the design is done, you have to construct it. You have to make sure you select the right type of materials. So a lot of laboratory testing is done, and that's where you need the basics of civil engineering learning to do the laboratory testing, to make sure it complies with the standards, and make sure the construction happens in the right quality, right? So this is how the loads gets distributed. And if you don't do that, what's going to happen? Your transport system fails. Now, if a road is like this, what happens? Your flow is no longer efficient. You're going very slowly. So a road there you could have traveled at 80 kilometers per hour. Now you're going at 40 kilometers per hour, and 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 uh, and that is not something, that is not what you call an efficient transport system, right? Right. So that is where the efficiency breaks down. So that's why you say we have to design a transport system in a proper manner so that it will function safely as well as efficiently. Right. So beyond our engineering domain, these are the few areas that transport engineers needs to have some idea, some awareness, or more than that, I mean, a little bit of appreciation of the implications of that. Road safety. A lot of our engineers have very little regard about road safety when they are designing infrastructure. So that is something that they should understand: vehicle performance, what it takes for a vehicle to stop, how your infrastructure will assist that, or will it assist that process, and the implications of that, especially the interaction between pedestrians and vehicles, who's at risk, and how do you minimize that risk. Environment and ecology, you'll see in the news a lot of problems when you do road projects. People are protesting. Environment groups are very aggressively protesting against some of the projects. So you have to acknowledge that there's a problem, and be ready to face those as well, because ultimately it will come down to the consultants or the contractors to defend those, right? Economics and appraisal, how do you justify these projects? Is it worthwhile constructing a 4-lane road? Do we need a expressway here? Should the government import these low-flow buses? So those are all economic decisions. And unfortunately, sometimes transport engineers are not that involved in those decision-making process, because we don't make ourselves aware of these components, right? We are just sticking to our domain, which is not enough. Equity and access, if you go to World Bank or ADB funding, this would be their number one criteria, it's equitable. Since my power is down, I will keep the video off. Don't mind. Right? So is it equitable? Does it serve the community, as considering the amount of money that you're investing? So this is where I feel our civil engineering graduates who go into the transport sector is quite behind. They are not appreciative enough of the broader impact that their design, their proposals will have on this environment, equity and economics, right? So we have to create more awareness in these areas. Right. So this is a good example of that. Is quite a famous accident in Passara, where a bus fell down that road, and then a lot of people died at that time. And people are questioning who is at fault here, who is accountable. Is it the government? Is it the bus driver? Is it the lorry driver? Is it just an unfortunate accident? Or who is accountable? Right. Ultimately, the people suffered. Right. So you realize that this is a design problem as well as an operations problem. Why is it a design problem? Is that you can see that same road about 6 years ago, you upgraded that road, you give indication that you can go fast, right? But you did not give the supportive infrastructure. If something happens, protective infrastructure to safeguard the people, the road users. Also, you realize there's a maintenance problem. That means during, you can see on the first top left-hand one, there's the lane is partially closed because there's an earth slip and the lane is closed. So the maintenance, there's no warning sign, there's no speed reduction sign, nothing is there to warn people that, okay, there is something going wrong here, right? So operations also part of transport system, right? So if you fail to operate it properly, you will also have these consequences. So of course, that's not the only reason that the driver was fatigued and all those were there. But within our domain, we should be mindful of what we can control and address those properly, right? So that's part of how transport systems should be designed. Right. So what do we do? I mean, some of you all might be closer to graduation. I think that this is something that I want to reiterate a lot because always the common misconception is that we just have road work to do. But there are a lot of career paths, for transport engineers to actually do. And right now, if you look at Sri Lanka situation, we are struggling in most of these areas, right? Especially traffic engineers. We do not have a lot of traffic engineers working in the industry. We have very few transport planners, working in feasibility projects to figure out, okay, how do you estimate the demand? How do you model this network? We don't have many. We do have some highway design engineers because there's a lot of people at RDA or PRDAs who are quite good with highway design. Transport modeling, again, very few in the industry, but there's a lot of demand, especially when you are starting new projects. We need to know about what is the outcome of various decisions we make, and for that we need a transport model. Moving ahead, there'll be a lot of demand for ITAs and data engineers in network level analysis, working with various other sensors and other big data sources coming in. Public transport specialists now, with a lot of these bus companies trying to be more professional in the way they're operating. There might be a demand to have qualified people helping those companies to plan and schedule their bus operations in a more scientific manner. Right now, it's not done in that manner. Going slightly away from our main domain, you go into logistics companies, go to ports, airports. Still, there are a lot of civil engineers working in Sri Lanka Ports Authority, Aviation Authority. And of course, you can work more as a researcher and academic like us, working on transport research, going into university. There are a lot of consulting companies hiring researchers to do advanced modeling, that type of work. There are a lot of institutions like NGOs doing policy-related work where transport engineers do work as a research. So a lot of career paths for transportation area. It's unfortunate that very little awareness is among civil engineers that there are all these opportunities are available, but they are just traditionally looking at road building as the only option. Right. So what do you need to do now? Now this is interesting. I purposely said relearn mathematics because my experience is that the way you have learned mathematics, I don't want to generalize, but majority of you, the way you have learned mathematics to enter the university is not helpful for you to practice as an engineer. So you have to figure out a way to relearn mathematics the way it's supposed to be learned. And students are struggling with the quantitative part of engineering because of this. So relearn mathematics because transportation is a lot to do with mathematics. Programming, being familiar with the software and coding, now things are easier with AI, but still you have to have some basic knowledge. You have to be prepared to go to the field. You can't become a transport engineer in office.
You have to be prepared to travel around the country, go to sites, see what's happening. And that's the best type of education you can get by observation. You have to go there and look at a junction for a couple of hours. Sometimes you might see a pattern, right? You'll get the opportunity to travel the world because transport projects happen across the world. So if you join a good consulting company, there's a lot of opportunities to travel to many parts of the world. So that's one good thing about transport. You'll be able to travel. So a lot of field work is involved. If you have time, if you are in the first, second, third years, do a final year project with some real data, laboratory test thing or survey related data that's just gives you a feel about what is really going on. And reading standards and specifications. Now I keep noting that students do not even know about the standards, let alone read about it. So you have to familiarize yourself with these standards, your design standards, like in structural engineering, so that you sort of understand what's going on. And a lot of these ISL sessions, student conferences like this, helps you a lot to gain a broader understanding of this field. Now, CILT, which I am part of as the president, we organize a symposium every year. About 30, 40 students studying supply chain, logistics, transport come and present their work. It will be nice to have, people from, students from civil engineering as well to come and present. So last year we had quite a good turnout from civil engineering students. Because it's all within the same broader domain. So it's nice to listen to someone talking about supply chain or logistics as well to expand your understanding. So please, as much as possible, take these opportunities when presented. Unlike a few years ago, when we were studying, we hardly had these sessions, but now I see almost every month there is one or two forums or conferences or happening. So at least if there are online opportunities, try to join because that will really gives you, it will be eye opener for you, right? So that's what you might do to see the opportunities. Okay, if you really want to specialize, of course, there's postgraduate program at Moroto. We do a master's program in transportation. Now I think our intake is like close to about 80 students per 2 years. So that's quite a large group. There are a lot of good schools for postgraduate studies in Asia as well as Europe. Of course, American universities still lead in terms of transportation engineering research. Once you get into the industry, you can get your professional qualifications through ISL. You can get your charter through CILT. That is, if you're in the public transport sector or transport management related sectors. You do consulting you join a consultancy company, get some experience. A lot of short courses offered by these professional bodies like ISL. You should register and follow those and get yourself equipped because your civil engineering degree will not give you cover most of the topics. It will give you the basics, but you have to keep updating your knowledge through these and then build your career as a transportation engineer. Right, so these are some of the tools available. I think some of you are already familiar with it. Now it's very easy. Now, for example, Sumo, that's open source software, very good software. Now with AI, you have a lot of these tools that where you can just prompt various, you don't have to code it anymore, right? So the prompts are there for you to use this software very easily. So unlike before, access to good software is now better. A few years ago, all the good software were licensed software, but now I see GIS, even GIS, traffic modeling, transport planning software, all open source software is available for you to learn. So make use of this opportunity and expand and Yeah, sorry, I got logged out. So I'm ending. Yeah, so main component for civil engineering is the fixed facilities. And there are a lot of opportunities. I think be open-minded to see where this is, where the opportunities are. And then Sri Lanka needs more transport engineers and we have to start producing, otherwise not only the sector, but the entire development program will suffer if you don't have enough transport engineers. So that's why I was very happy when Professor Subramaniam invited me to do the keynote, because that will give me a chance to promote a discipline that I am very passionate about. Right. Thank you very much. Okay, right. Thank you.
Distinguished keynote speaker, Professor H.R. Pasindu, for accepting our invitation and delivering such an insightful and inspiring keynote address. Your valuable perspectives, professional experience, and thoughtful observations have added immense value to today's symposium and have encouraged our young researchers to approach engineering challenges with greater curiosity. Our sincere thanks are extended to the Chief Editor, Engineer Sajivan, for the dedication, attention to the details, and academic commitment demonstrated throughout the preparation of the symposium proceedings. The successful completion and publication of the proceedings would not have been possible without your leadership and careful coordination. I would also like to acknowledge the President of Civil and Environmental Engineering Society for the leadership, commitment, and continuous coordination provided throughout the planning and execution of this event. Symposium is ultimately made meaningful by the research that it presents. Therefore, I extend my warmest appreciation to all the undergraduate authors and presenters who have shared their works today. Your research reflects the knowledge, effort, perseverance, and innovative thinking developed throughout your undergraduate studies. I also congratulate you for confidently uh, going to present your findings and responding to the questions. So we gratefully acknowledge the academic staff members, research supervisors, co-authors, and reviewers who guided the students, evaluated and submitted the work, and offered constructive recommendation to improve the quality of the abstract, papers, and presentation and proceedings. My sincere appreciation also goes to every member of the Symposium Organizing Committee in the Civil and Environmental Engineering Society. From coordinating submissions and correspondence to preparing the venue, registration, program, publication, technical arrangements, hospitality, photography, and documentation. Your collective effort has made today's event possible. We also thank the administrative, academic, technical, and non-academic staff members of the Department of Civil Engineering and Faculty of Engineering for their assistance and cooperation throughout the organization of the symposium. Our gratitude is extended to all invited guests, heads of the departments, professors, lecturers, students, participants, and members of the audience for joining us today. Your presence, questions, observations, and encouragement have made this event both engaging and memorable. Finally, I would like to thank everyone who contributed to this symposium in any capacity, including those whose efforts may not have been individually acknowledged. Every contribution, whether visible or behind the scenes, has played an important role in the success of this event. On behalf of the Civil and Environmental Engineering Society and the organizing committee of the third Undergraduate Symposium 2026, I once again extend our sincere gratitude to you all. Thank you, and I wish everyone a pleasant evening ahead.
Thank you, Mr. Resignation. This brings our opening ceremony to a close. Without further ado, we begin the technical session of Symposium 2026, where our researchers and students will present their work on the multifaceted concept shaping civil and environmental engineering. It is my pleasure to introduce our session chairs, Mrs. P. Sangeeta and Mr. S. Kishodaran. Please join me in welcoming our session chairs to the podium. We have 10 oral presentations followed by a Q&A question. Each presenter is requested to complete the presentation within 6 minutes. The time indication will be given when 1 minute remains. To maintain the program schedule, all questions will be taken during the general discussion after the completion of all 10 presentations. I kindly request the presenters to remain in the schedule order. Let us now be able to sit. The first based on three of mine. I want Mr. Ishmael and Mr. Itamani.
So welcome everyone. So here we are come here to present our research presentation on application of custom convolutional neural network for aggregate shape classification based on degree of milling. So aggregates are the coarse material used in the civil construction site. So normally within the milling classes, within the depending on the type of requirements, the level of milling of the aggregates will vary. So during the milling process, what happened, the physical property and morphological properties of the aggregate get altered. So here we are going to use the Los Angeles abbreviation machine for this milling process. So here we are using 6 classification classes. One is 0, 100, 500, 1000, 1500 and 2000. So those 6 classes are present in the slide. So here let's discuss the previous studies done in this classification of aggregate. So normally they have used images software for the shape parameter to finding the 14 shape parameters, and they are using those as a features for the ML based classification and statistical shape analysis, and they are also using the Fourier shape analysis for this aggregate shape classification. So what is the they are best at classifying the binary classification, whether it is milled or unmilled, but when coming into the multi-class classification, the accuracy very low. So here we are going to polish our research by increasing the accuracy of multi-class classification, and so far they have not been used the CNN based classification in this particular field. So we are going to employ the CNN based classification. So normally for the aggregate shape classification, they are using the handcrafted features as a features, but here we are going to employ the CNN based features. CNN based features to classify, and we are going to deliver a lightweight custom CNN model with a lesser inference time for the apps, which is working good at working in the robust environments. So we are using the data set that were used in the previous study. So totally 15,000 images were used, as totally 6 classes per class, 2,500 images were used. So as the previous studies are focusing on the boundary analysis, so here we are mainly focusing on the morphological and textural features. So here we are employing a contrast limited adaptive histogram equalization as a pre-processing method to enhance the morphological and the textural features of the raw image. So the block diagram show how we have extracted the features. So after the pre-processing, we are splitting the data set as a training, validation, and testing data testing, and we will train the 8 custom model using the training data set. And after that, on the models which are performing best, we select those model and use feature selection to extract the deep embeddings from those custom models and use those as a features for the SVM based classification. So the performance of our models will be evaluated based on the accuracy, precision, recall, F1 score, and inference time, and the model size. So when it comes to the data set, we are using totally 10,500 images as for training, and 1,500 for the validation, and 3,000 for the testing. So this is the configuration we are using for the 8 custom model and the 8 hybrid custom models. And coming into the hybrid models, we are using the deep embeddings that are obtained in the custom model as a features, and using the mutual information and MR for the feature selection, and doing an SVM based classification. So let's how we come to the results. So this is the 8 convolutional 8 custom models. So here the model which having the 6 convolution layer model having the higher accuracy, about 82%. So you can see the image of the convolutional layers. So here you can find out the custom model with the 6 convolution layer is best performing.
Thank you, Noiska. So let's talk about the key findings and results. So this is the standalone model and its accuracy. So its accuracy about 82.2%, and the hybrid model that we have used MRMR feature selection and SVM for the classification, which have increased accuracy of 82.3%. And this is the precision and recall for the particular standalone model. As you can see, the extreme classes such as 0, 100, and 2000 have really good accuracy, but you can see in the intermediate milling classes, we have the low accuracy. It's because of due to its small subtle morphological change during these milling classes. That's why this model has find this hard to distinguish these uh, milling classes, and the hybrid model also follow the same pattern. And this is the confusion matrix. As you can see in the confusion matrix, we have a strong diagonal. Even though we have strong diagonal, you can see the 9 blocks. Uh, we have the milling classes have confused with each other. And let's talk about the key findings. So CNN6, among the 8 convolutional models, the CNN6 have best standalone performance, and this best hybrid model also increased the accuracy. And the XCM classes such as 0, 100, and 2000 have classified reliably, where the intermediate between classes is hard to distinguish. And increasing the depth beyond the 6 convolutional level, which won't help us to increase the accuracy or even reduce the inference time. So in conclusion, so we have successfully classified these 6 classes into by custom CNN, and compared to large pre-trained models such as ResNet 50 and efficient net, we have lightweight CNN can reduce the computational cost drastically, and we can deploy in the microcontroller as well. And this MRMR and SVM hybrid approach have improved our accuracy as well. And this proposed approach show potential for automated aggregate quality control. And our future work would be say, like explore the further lightweight and attention based model and validate our system with real industrial environments. And
Thank you both. So now we can move to the second presentation, which is geometric shape descriptors for aggregate classification. I would like to invite Mr. K. Rishikeshan to deliver the presentation.
good evening, everyone. So myself, Rishikeshan. So I'm here to present my extended abstract titled Geometric Shape Descriptors for Aggregate Classifications. So let's move to the introduction. So why aggregate morphology matters? So the aggregate shape is one of the crucial thing which determines the performance of any construction materials, given that it contribute to the strength transfer and the permeability of the construction materials. So the current simulation models are approximating the aggregate shape as spherical shape. So it actually tends to go towards a point contact between the aggregates, and the shape measurement is actually manual calipers which reduce 3D morphology to limited ratios. So the whole research is based on a question, which is, can image derived morphology descriptors and graph learning identify meaningful process phases in mill aggregates? So to answer this question, the experimental workflow is uh, constructed as we first get the gneiss aggregate from the northern part of the Sri Lanka, and we uh, make through the law milling, and then the sill out imaging, and then we extract 14 shape descriptors, and we form a KNN similarity graph, and then a GNN phase classification is performed. So to talk about the data set and the descriptor space. So first, when we are collecting the images, we will have a white sheet where the aggregates are placed. So to reduce projection bias, we are rearranging the aggregates 10 times and taking 10 images for a single group of aggregates. So this makes the projection bias reduced. So then altogether we are getting 36,000 aggregate particles, where each revolution have 3,600 particles. So as you can see, we are considering 0 to 1,500 revolution levels, and then we will get 14 geometric shape descriptors for particles, and the aggregates are between the 5 and 18 millimeter wet particle. And then each aggregate is taken as a node, and morphological similarity between these aggregates are formed as the edges, and then the node feature vector is constructed as the node features are all the geometric shape descriptors. So that fed into the GAT V2 attention layer, and then the phase probabilities comes. So first, the initial model screening, we first approached a 10 flat class revolution classification. So then if you see that the random baseline is 10% and we obtained 25% of 10 class GNN screening. So this might be lower, but it's actually above the random baseline. And then we tested many GNN architectures, and everything is fell into the shown range. And then GATV2 is the selected one because it has the consistent performance with the weighted cosine edges. So then to analyze further, we went into the statistical analysis. So we first approached an ANOVA where we got the descriptor means, which is plotted here. So this plot is actually only for the Cepheid subsets came between 6 to 7. Those shape descriptors are only plotted here. So you can see that the larger step happened in the transition where it goes from 100 to 150. So it almost 4 to 8 times steps. So then we also analyzed the Cepheid subsets where we got from 3 to 5 shape subsets, geometric shape descriptors. So you can see that from 750 to 1500, it constantly grouped together. So it means that there is another boundary. So altogether, we identified two boundaries: a primary boundary between 100 and 150, and then a secondary boundary 500 to 750. So we made a partition scheme, and the S1 is the partition scheme consisting that identified primary and secondary boundaries, and then we checked it with random boundaries and random partition schemes. So you can clearly see that the S1 final, which is the derived partition scheme, is the best performing. And also S2 had 76.7 accuracy, but you can see that the phase one completely collapsed. So it acts like two class classifier. So it's not mean anything. So then this is the morphological meaning and the findings. So this give discrete transition and transition overlap and late smoothing. So the conclusions are there are two primary and secondary boundaries exist, and then the statistical motivated partition is the best performing partition scheme. So the future direction could approach where we can get 3D projections of aggregates or surface texture features, or more meaningful shape descriptors like Fourier or any other method to capture the contours. So thank you.
Thank you, Rizikeshan, for your clear presentation. So now we move to the third presentation. Title is Genetic Genetic Algorithm-Based Adaptive Spectral Topology Optimization for Detecting Morphological Changes in Bowl Mild-Nice Aggregates. I invite Mr. A.P.A. Thorless to deliver the presentation.
Good afternoon to you all. I am Abhishek Carlos. My research is genetic algorithm-based adaptive spectral topology optimization for detecting the morphology changes in the ball mill aggregates. First, I would like to introduce my research. Aggregates are used for the construction. So, aggregate morphology significantly affect the performance of the perfect and concrete materials. So, for during the ball milling, that changes the shape and the surface of the characteristic of the aggregate. So, for detect that one, we are using the Fourier shape analysis, but individual frequency scripts are higher much of them. So that one making it difficult to effectively represent the morphology sensitive information. For that one, we come up with a study genetic algorithm based adaptive frequency banding approach to group related frequencies and improve the detection of milling morphological changes. For do that one, we come up with an objective. The first objective has to be develop an algorithm-based frequency bending approach to optimize grouping the Fourier descriptors. From that one, we are like to extract the features from the optimized adaptive frequency bands to effectively represent the aggregate morphology. Then, using that one, we are like to evaluate the effectiveness of the proposed adaptive frequency banding for classifying different milling stages using the classification methods. So for doing that one, we come as the methodology as first we have like done the data collection and processing. As you can see in the figures, the aggregates are get from the northeast part of the country. Then that has to be milled on cloud machine. Then there has to be made as a raw image. Then that image has to computation method that has to be binarized as is in the figure. Then from that figure we have extracted the boundary of the shape. Then that shape has to be sampled as seen in figure. Then that sample has to be made as the 2D signal. Then the 2D signal has to be transferred the Fourier components using the digital frequency transformation. This is our data getting method. We have classified using the multiple method, but here the genetic algorithm analysis is the major one. So here we have to divide as the band. For that one, we have taken as a chromosome as the four frequency range. There we have taken every gene as the frequency boundary. Then from that boundary, we have extracted the statistical features. Then that has to be classified using the extract classifier. So doing that one, we have get our fitness function. Using that fitness function, we have selected the parents that has the crossover and mutation. Then from that one, we get the new genome generation. Then we have checked for the conversion of the algorithm. If conversion, there will be n. Otherwise, it has to be processed to get the proper and optimized frequency band. So from that things, we have get our results. As you can see in the figure, the fitness function has to be improved from the 0.471 to 0.586. Also, you can see in the figure, the accuracy also improved from the 49.39 to 53.31. So, this indicates the algorithm has to go towards the convergence behavior. Also, these things are done within the 90 generation. So, the algorithm has converged within the better way to nearly install. So, we get another results as the frequency band. As I was expecting, we have gone to find frequency band. As you can see in the figure, we get the 6 frequency bands. The 552 descriptors are make it as a 6 frequency band. So, as you can see here, the lower frequency are as a multiple dividing has there. But for the higher frequencies, there may be a large deviation. This indicates that the information concentration within the band, the lower frequency has contained the higher band, the higher frequency has expecting to have the larger information, lower information. So also we have extract the statistical features from the band we have find. So like mean, standard deviation, RMS, energy, maximum range, these kind of standard features are we are extracted to give the meaning to the band. So by getting this one, we have reduced the future dimensionality. Also, we have grouped the frequency band and preserve the morphology information. This also help us to improve classification performance. Also, we have get the confusion matrix for genetic algorithm. As you can see in the figure, the extreme milli stages of the weighted classification. For the 0th revolution, you can see that it has to be more darker, and also 2000 revolution also more darker. It indicates that the large extreme stages are weighted classification. Also in between there also we have some overlapping, but the this indicates that frequency classification using genetic algorithm has identified there will be a separation that identification has been explained there. Also, we have get this using the overall accuracy 53.31 and F1 score 51.99. So from these all the findings, we can come to the conclusion. So the genetic algorithm successfully identified for the lower band with the higher for indicating the Fourier descriptors effectively. So this adaptive frequency bands effectively present the shape and the texture information and roughness, providing more meaningful features for the differentiation of the frequency band. And also the extracted features then the accuracy 53.31 has indicate that there is changes in the frequency for the morphological changes. By using these all things, the proposed adaptive spectral topology framework provides an effective approach to detecting milling-induced morphological changes in its aggregates. Thank you.
Thank you, Taurus, for sharing the finding of your research. Let us proceed to the fourth presentation, Structural path modeling of pervious concrete against aggregate size. I invite Ms. A.R. Mary Evansica to deliver the presentation. Good evening, everyone. I am Yvonne from the Department of Civil Engineering. Today, I am presenting my research entitled Causal Path Modeling of Pervious Concrete Against the Aggregate Size in Pervious Concrete. This research investigates how the aggregate size and convection influence to the compressive strength and the porosity by using the weighted standardized causal path model. First, let me introduce the pervious concrete. Pervious concrete is a special type of concrete containing interconnected voids that allow water to pass directly through the concrete. Because of this property, it offers several environmental benefits, such as it improves the groundwater recharge, reduce the stormwater runoff, and supports to the sustainable pavement system. However, there's a major challenge. The increasing porosity will improving the permeability. At the same time, it will reducing the compressive strength as well. Therefore, achieving an appropriate balance between the compressive strength and the porosity is a significant engineering problem. This motivated me to do this present study. The objective of my research are to investigate the influence of the aggregate size on the compressive strength and the porosity, to study the effect of the convection, to develop a weighted standardized causal path modeling, to identify the optimum aggregate size and the convection that provide the best balance between the compressive strength and the porosity. And finally, to quantify the direct, indirect, and total effects. Here, the ordinary Portland cement and clean water were used. Also, the 5 aggregate size configurations were analyzed, the picture shown here. Throughout this experiment, the water cement ratio was kept constant at 0.3, while the AC ratio varied from 2.5 to 7. If we move on to the part of methodology, it consists of 2 phases. At the first phase, initially all materials were throughoutly mixed to obtain the uniform mixture. Then the mixture was placed to the 150 millimeter cube molds. After that, the convection was carried out by using the standard Proctor hammer with different convection from 0 to 60 block. After that, the surface was carefully finished. Then the specimen were cured for 28 days. Then our specimen were ready for the experimental testing. Here the wet density, measured porosity, and the compressive strength were found. Finally, the experimental data were analyzed using the weighted standardized causal path modeling to evaluate the relationship among the variables. This model consists of 3 categories of variables. The input variables are the AC ratio and convection. The mediator variables are the wet density and measured porosity. And the output variable is the compressive strength. It's unlike the ordinary correlation analysis. It helps to quantify the direct, indirect, and the total effects.
The results indicate that the A05 range from 2.36 to 5 millimeter exhibit the higher positive total effect. Also, the A03 and A04 showed the positive contribution, but A02 produced the negative effect and the total effect due to the unstable poor connectivity. These findings indicate that the small aggregate size improve the packing density and the internal stress transfer. It's result the better mechanical performance. The causal analysis show a different influence for the each variables. So the aggregate cement ratio produce the direct effect. In contrast, the convection produce the positive effects. So the control convection significantly improve the compressive strength by enhancing the weight density and reducing the excessive porosity. The weighted standardized causal path model showed a strong explanatory capability. The adjusted R squared values were approximately ranged from 0.7 to 0.9. These high values indicate that the model effectively captured the relationship among the experimental variables. Overall, the study demonstrated that the aggregate size significantly influenced the pore structure formation. The smaller aggregates improve the packing density and the compressive strength. The controlled convection enhanced the weight density and decreased the excessive porosity. In conclusion, aggregate size and the convection significantly affect the performance of the pervious concrete. The weight density and measured porosity are the key mediating variables. Here, the A05 demonstrate best overall value. And finally, the weighted standardized causal path model is an effective tool for optimizing the sustainable pervious concrete mix design. Thank you very much for your kind attention. Thank you.
Thank you, Ivansika. So now we will move to the next presentation, which is investigation of binder distribution in pervious concrete. I would like to invite Mr. S. Vignesh to present.
Good afternoon. I'm Vignesh. Today I'm going to present my research titled Investigation of Binder Distribution in Pervious Concrete. Pervious concrete is widely used as a sustainable pavement material because its interconnected pore structure allows stormwater infiltration and groundwater recharge. However, its performance depends not only on porosity, but also on how the cement binder is distributed around the aggregate skeleton. Although previous studies mainly focused on compressive strength and permeability, so limited attendance has been given to the internal binder distribution. Therefore, the study investigate how aggregate abrasion and convection influence the binder distribution using image-based analysis. The main objective of the study was to investigate the binder distribution in pervious concrete using image analysis. 3 aggregate to cement ratio, 3 aggregate abrasion levels, and 3 convection levels were used. For each one, we get 2 samples, so totally 54 specimens were prepared for the study. First, aggregates were subjected to 3 different abrasion levels, 0, 200, and 1000 revolutions. After abrasion, the aggregates were wet sieved to obtain the required size range of 12 to 25 millimeter range and then air dried. Next, pervious concrete specimens were prepared using 3 aggregate to cement ratio of 3, 4, and 5. A water to cement ratio of 0.3 was maintained to achieve a zero slump concrete mixture. Then the specimens were compacted using 3 compaction levels, 0, 30, and 60 blows. In total, 54 concrete specimens were prepared and cured in water for 28 days. After curing, the core samples were extracted from each concrete specimen. To improve the image quality, the matte varnish was applied to seal the small surface pores on the aggregates. Then the white pore filling material was applied to the surface pores, visible surface pores. Finally, the panoramic images of all core samples were captured for image analysis. The panoramic images were processed using a Python-based image analysis program. First, each panoramic images was converted into binary image, where the black region represent the binder and white represent the aggregate and pores. Next, the binary image was divided into 10 equal horizontal layers from the top layer to bottom layer. Then the binder fraction was calculated separately for each layer. The Python program automatically generated an Excel file containing the binder fraction values for all 10 layers of the specimen. Finally, these data were used to evaluate how aggregate abrasion and compaction influence the depth-wise binder distribution in pervious concrete. This figure shows the effect of aggregate abrasion on binder distribution at an aggregate to cement ratio of 5 and a compaction level of 60 blows. The green line represents the 0 revolution, and the blue and red lines represent the 1000 revolution and 200 revolution. We can see that the specimen without the abrasion shows lower binder fraction throughout the specimen depth. In contrast, the specimen with 200 and 1000 revolution show higher and more uniform binder distribution. This is because the aggregate abrasion makes the particles more rounded. The rounded particles improve particle packing and allow the binder to spread more evenly throughout the specimen. Therefore, the aggregate abrasion mainly affect the spatial distribution of the binder rather than the overall binder fraction. And this figure shows the effect of compaction on binder distribution at an aggregate to cement ratio of 3 and aggregate abrasion level of 1000 revolutions. The blue line represent the specimen without compaction, while the red and green represent the 30 and 60 blows. The specimen compacted with 30 and 60 blows show higher and more stable binder distribution compared with the specimen without compaction. The specimen without compaction shows larger variation because the concrete had 0 slum mixes. Without compaction, the aggregate arrangement depends mainly on random mode filling, resulting in a less uniform binder distribution. Therefore, compaction helps to produce a more stable and uniform binder distribution throughout the specimen. So, conclusion. In conclusion, this study successfully investigated the binder distribution in pervious concrete using Python-based image analysis method. The results showed that aggregate abrasion improved the uniformity of binder distribution, while compaction produced a more stable binder distribution than specimen without compaction. The layer-wise analysis also showed that binder distribution is not uniform throughout the specimen depth. Overall, this image-based layer analysis provides useful information about the internal binder distribution that cannot be obtained from the overall binder fraction alone. And these are the references I use for this study. Thank you.
Thank you, Vignesh. Let us now proceed to the sixth presentation, which is correlation analysis of the thermal response in porous concrete using T90 and delay parameters. I invite Mr. J. Washington to deliver the presentation.
Good evening to you all. I'm J. Kumar Vasan from Department of Mechanical Engineering. And today I'm here to present my research titled Correlation Analysis of Thermal Response in Porous Concrete using T90 and delay parameters. Now let's look at the small background of this study. The porous concrete was made by the normal way of the conventional concrete, but without adding the fine aggregate. Without this fine aggregate, there is a gap between the coarse aggregators. And due to the gaps, its ability, the main ability of here letting the water passes through it. So it's mainly used for the pavement applications. and mainly used for the payment applications to avoid the flood in the urban areas. But it can also we can use as an on-load bearing walls. When it is used as a wall, the ability of transfer the heat of the wall is more important to better maintain a better thermal comfort inside the building. So there are several models have been used to evaluate the heat conduction properties of the pore materials, but it also have some limitations like ideal post structure or avoid the thermal boundary resistance like that. So this study is mainly focused on the how AC ratio in the compaction influence the heat transfer ability of the porous concrete. And there's also some previous studies also conducted using counterplots to analyze these parameters. So as per the image, totally five sensors were embedded into the concrete specimen within the 50 millimeters interval. The sensors were named P1 to P5. So totally four AC ratios were considered 2.5, 3, 4, and 5. And also three type of compactions were given 0, 30, and 75 blows. The heat is given near to the P1 sensor, and all of the sensor readings were recorded using a ordinary based DAQ system. So using the uh, recorded data, we finally calculate the T19 and the delay parameters. The T90 means that for a sensor, the time taken to attain the 90 percentages of the maximum temperature, and the delay means that time taken to heat travel from one point to another point. It's calculated using the difference between the T90 values. And now we move to the results and discussion part. Um, this is the correlation metrics of T90 values, position P1 to P5, and the maximum values were obtained between T90 P1 and T90 P3, and the minimum values is obtained between the T90 P2 and T90 P5. So we can here clearly see a trend between the T90 P1 that which is heat given site. When the distance from the heat source is increasing, the correlation values were decreased to 0.89617 to the 0.7461. So this is clearly indicating when the thickness of the wall increases, inside temperature is mostly influenced by the internal post structure rather than the external heat source. So now we look at the delay correlation matrix for uncompacted conditions. We can see there is almost no correlation between the parameters. But when we given the distributed compaction for 30 blows, we can see the least amount of correlation is the 0.8080. That means the all of the values are greater than 0.80, indicating the much more dependent behavior on each parameters. So now, based on the results, these figures explain the heat transfer mechanism in the low or no compaction condition. Because of the large number of pores and voids, the heat follows irregular paths. As a result, the delay values show weak correlation, leading to slower and non-uniform heat transfer through the concrete. And in contrast, distributed compaction reduces the pore size and makes the pore distribution more uniform. This creates more continuous heat path, resulting in strong delay correlation, as we observed in the correlation matrix. Therefore, heat transfer becomes faster and more uniform throughout the specimen. And finally, to conclude, this study found two important observations. First, as the wall thickness increases, the internal temperature response became more dependent on the internal pore structure than the external heat source. And second one is higher and well-distributed compaction reduces pore size, improved thermal connectivity, and produce more predictable heat transfer with strong delay correlation. And thank you.
Thank you, Washington, for your informative presentation. Let us move to the next presentation titled Aggregate Morphology Evolution under Progressive and Direct Milling Using Fourier Shape Descriptors I would like to invite Mr. A.R.M. Rifti to present the finding of the studies.
Good evening, everyone. I am Rifti. Today I am present my research entitled Aggregate Morphology Evaluation under Progressive and Direct Milling using Fourier Shape Descriptors. This study investigates how aggregate particle shapes change during the milling and whether those changes depend only the total number of revolution or also on the milling history. Let's move to the introduction part. Basically, the construction aggregate are widely used in concrete aspect and road construction. Their shape directly influence taking efficiency and compressive strength, permeability, and fatigue resistance, like durability. The tradition, the engineers say the parameters, shape parameters such as circularity, roundness, and aspect ratio. Describe only a single aspect of a particle shape, not enough. So to overcome this limitation, we want to this research use the Fourier shape descriptors, which divide the particle characteristic into form like H1 to H5. The form angularity is the H6 to H16. Surface texture is the S17 to S52. Let's move to the objective part. The first one is compare the progressive and direct milling protocol using the Fourier shape descriptors. The second one is excess component wise NOR separability across all Fourier magnitude for both datasets. The third one is investigate path dependence using like PCA, rank correlation like this. The fourth one is identify which morphological zone are most sensitive to milling protocol. Let's move to the methodology part. This is the workflow I choose. For this research, the genius aggregates are from North Central Sri Lanka were selected. The size is 5 to 25 millimeter. The particle were washed and sieve 5 to 80 millimeter and the photograph using a camera under control condition. The particle boundaries were converted into 512 Fourier component using a descriptor Fourier transform. The two datasets were prepared. First one is direct milling. Direct milling means where separate fresh batches were milled independently to each revolution level. The second one is the progressive milling. Progressive milling where the same aggregate which was milled continuously from 0 to 500 revolution. Let's move to the data analysis part. The Fourier component were grouped into form, angularity, and texture, and the analysis using ANOVA and TECI, HST, BCA, the rank correlation, the delta, and the effect size plus distance. Likewise, we analyze the data analysis part. First one is ANOVA and result. ANOVA result, all Fourier components change significantly throughout the milling process. The texture zone recorded the highest F values, indicating that surface roundness is the most sensitive characteristic is the effect by the abstraction. The Turkey HST also showed that the adjacent milling stage such as 50 to 100 revolution were often not significantly different. This indicates that the morphological evolution occurs through the gradual stages rather than the changes at the constant rate. Let's move to the F value separability. One of the most important finding is the correlation of 0.96. This indicates very strong agreement between the progressive and direct milling, regarding which Fourier component best distinguish the milling stage. However, form and angularity component rank much as higher progressive milling. This means the progressive milling preserve gradual shape change that direct milling tend to suppress. Let's move the PCA analysis. Here, the 60.76% of the total variance there. Although statistical tests showed the significant difference between the dataset. The PCA cluster largely overlap. This suggests that both methods follow a similar overall evaluation pattern, but the milling history still influences the details of morphology, and the LDA accuracy of 53.7% is indicate only the moderate separation between the two dataset. These are the key findings. Rather, the final particle shape depend on not only on the total number of revolution, but also on how the particle reach that stage. The progressive milling preserve intermediate shape changes while direct milling compress these changes into fewer stages. However, the texture zone remains a stable indicator of abstraction in both milling methods. So the conclusion, these are the reference I use. Thank you.
Thank you, Rifti. Let us proceed to the eighth presentation, investigation of the impact of aggregate size on porosity and compressive strength of pervious concrete. I would like to invite Mr. K. Lojidas to deliver his findings.
Good evening, everyone. I am Logidas. Today I am going to present on investigation of impact of aggregate size on porosity and compressive strength of pervious concrete. Pervious concrete is a sustainable concrete. It's allowed to the water can pass through the interconnected voids, and it's mainly used to the pavements and low traffic areas and parking areas to reduce the surface runoff and improve the groundwater recharge. And PC has a low compressive strength. It has and durability. It has a high porosity. And in this case, I investigate how to aggregate size and compaction energy influence to the porosity and compressive strength. And also, I developed the machine learning model to predict the machine compressive strength. This slide show my XML works, and first I use the materials aggregates cements waters, and the water cement ratio is kept to maintain 0.3, and we use the different AC ratios 2.5 to 7, and we use mix proposing and 5 different aggregate size, and I also used the 3-layer compaction. Used the 0, 15, 13, 45, 16, 75 compaction blows. And after that specimen, we are queued 28 days, and finally we find the compressive strength and porosity. Next, the XML data, we are used the machine learning models. Firstly, data is cleaned and organized input output variables. Then we divide the 3 variables design only. Design only means only use the mixed design parameters, aggregate size, compaction energies, and the interim only measured use the measured properties, porosity and bed densities, and both are mixed to calculate the design plus interim. Then we used 9 machine learning models, and the models we are compared to using the model evaluations to select the best models, R squared, RMSE, MAE, and MAP. This list shows the effect of aggregate size on compressive strength, and this result shows how to aggregate size are impact to the compressive strength. And smaller aggregate size have a higher strength because the particles are packed together, and larger aggregates creates more weight, so concrete has a lower compressive strength. Also, increase the compaction blows generally increase the compressive strength. This list showed the relationship between the porosity and compressive strength. You can see the graphs. If the porosity is increased, the compressive strength is decreased. This is because more porous reduce the contact between the aggregates. And so it's important to keep good balance between the porosity or compressive strength. This slide shows the results of LS boost model. This is the best of models. The model gave very accurate predictions. It achieved to R-squared values 0.998 and RMSE values 0.492 and MAS values 0.214 and MAP values 1.87. And this predicted values, we are close to experimental values. This shows the models can predict the compressive strength very well. Then, first, the LS boost model was optimized to improve the prediction accuracy. During the turning process, the validation RMS remained low, which means the model becomes stable and reliable. Also, the model shows the very good performance for the predicting new data. You can see these are the turning trials. And finally, the conclusion part. Aggregate size is an important factor to affect the both porosity and compressive strength. And small aggregates increase the strength, while large aggregates increase the permeability. So higher compression improve the strength, but too much compression may reduce the pore connectivity. Finally, among all the machine learning models, design influence in interim strength configuration with the LS boost model gave the best predictions performance. These are the reference. I use the slides, and thank you.
Thank you, Logitas, for sharing the findings of your research. Now we will move to the ninth presentation, evaluation of aggregate morphology evolution under controlled milling using statistical and machine learning techniques. I invite Mr. A. Karnan to deliver the presentation.
Good evening to all. I am Karnan. Today I am going to present on evaluation of aggregate morphology evolution under control building using statistical and machine learning techniques. Let's move to introduction. Aggregates are fundamental backbone of concrete. It's spanning from fine sand to coarse, and also in the concrete strength and permeability and durability, it's affected by the packing efficiency. The packing efficiency is rely on the aggregate shape, but in the mixed design, they rely on the ratios, but they overlook the aggregate shape due to its complexity. So that the numerical shape representation need to use in the mixed designs. And also now they are using circularity, aspect ratio, and specificity, but that is a lack of precision in capturing the variation that influence the properties. So that the aim of this study is to determine which geometric shape descriptor most accurately define the aggregate shape. To achieve this, we have three objectives: to analyze the geometric shape characteristic of aggregate across the different milling revolution, to determine the key shape descriptor that influence aggregate classification, to establish the classification framework for the aggregate shapes. Next, move to the methodology. Methodology have the four major parts. First one is the control milling. By using the Los Angeles abrasion machine, aggregates mill at 0, 50, 100, 150, 200, 300, 500 revolution. And after this process, then image processing process. For the image processing, we use Sony Alpha 7 III camera to camera. Then for the binary changes, we use FPGA and MATLAB for the binary images. Then after that, major shape descriptor extracted. Then from that one, we calculated 14 major shape descriptors. After that, it's involved a statistical and machine learning analysis part. Next, look at morphology evolution under milling. When we look at this one, increasing the revolution, the aggregate getting more smooth and it's come to round shape. So morphology becomes relatively stable after extended abrasion. And these are the geometry shape descriptors in the studies. And this is a trend of the descriptors with increasing revolution. Here you can see circularity and convexity. It's generally increase with the milling because when it's get smoothing and it's losing the angularity, so this will increase. And also you can clearly see that one after milling the
we measured two different porosities, theoretical porosities and measured porosities. The theoretical porosity we calculate from the volume of cement and aggregate, and measured porosity we measured from the experiment. Then from the data analysis, initially the experimental result we get material testing, and under material testing we find the compressed strength and porosity. And for the statistical pattern analysis we did, and regression analysis also we did. Then mathematical modeling, we with porosity initially we find the compressive strength by using only the porosity. Then with including parameters with porosity we find the compressive strength. Then this from the resultant discussion, initially we find the measured porosity and the theoretical porosity. That measured porosity by using this equation we find we measure the wet density and the dry density. From that we find the measured porosity. The theoretical porosity we calculate according to the manual. And in the mathematical model, initially we used to find uh, predict predict the compressed strength by using the K6 equations from the only using the porosity. Then exponential graph shows the measured porosity versus compression. This accuracy is 0.57 we get. Then after that the predicted compression and measured compression we compare those things. From that we get that accuracy. Then after that we enlarge the update the equations from the literature review. This equation I get from the literature. From that we predict the compression strength and observe compression strength also we measure plot. According to that we get the accuracy 0.46 0.64. Then by using here we use the parameters as porosity, aggregate cement and convection in the study. Then after that we choose aggregate size and shape also. With that one we predict the compression according to that. Here we change the equations constants a and f. From that we calculate predict the compressed strength, and from that we plot observe and predicted. From that we get the accuracy of 0.92. Then from this conclusion, based on the result and result in the compress for the porous concrete, the porosity and compaction aggregates cement ratios, all the things will affect the compressed strength of porous concrete. From that from this equation we find predict the compressed strength of porous concrete. In here B, C, B and C, B, C, D and E are without change. Here we change only A and F, which are represent the aggregate size and shape of pervious concrete. Uh, these are the references I used to prepare the slides, and thank you.
Thank you, Sobachan, for the valuable presentation. So, ladies and gentlemen, we have reached the end of the technical session. On behalf of the symposium organizers, I sincerely thank all the presenters for sharing their research findings. I thank the academic supervisors and members of the audience for their attention. I thank Engineer Kishodran for his support throughout the session. Once again, thank you all. Have a pleasant evening and wonderful weekend. Thank you.
That concludes our lineup of oral presentation for this section. We extend our sincere congratulations to every presenter for the quality and depth of research shared with us today, and thank our section chairs, Mr. S. Kishodaran and Mrs. S. Sangeeta. Now we come to a moment of recognition of our presenters. We invite all presenting authors to please make their way to the stage to receive their proceedings. We invite our Dean Faculty of Engineering, University of Jaffna, to proceeding each authors to the certificates. First, I invite S. Nadishkar and A. Janarthan. K. Rishikeshan. APA Dallas. AR Mary Ivonshia. S. Vignesh. J. Washington. ARM Rifty. K. Logitas. A. Karna. J. Shobijan.
Thank you, sir. Congratulations to all our authors. Your contributions form the intellectual core of our Symposium 2026. And we thank you for the effort and dedication behind each piece of research presented today. As we draw Symposium 2026 to a close, we would like to thank our Dean and Head of the Department's keynote speaker, our sponsor, Tokyo Cement Company, Lanka PLC, and our presenters, faculty, staff, and each of you for making this event a memorable success. On behalf of the Civil and Environmental Engineering Society, University of Jaffna, thank you for being part of this journey through the multifaceted concept, and our sincere apology and sorry for the technical errors that occurred in between our program. And thank you for your patience. We wish you a wonderful journey home and look forward to welcome you again for our future events. Thank you very much.